There are two coils A and B which are kept next to each other, and current is decreasing in coil B with time. Now we can see these two coils in front of us, and there is some current in coil B, and that is supposed to be decreasing with time. The first part is considering the effect of current induced in coil A. Will these coils attract or repel? And the second part is what is the direction of induced current in coil A. Now let's focus on the first part to begin with, and we will come to part 2 later. And also for a common perspective between you and me, let's say that the shiny part of this coil is towards us, which means this node P will be towards us and Q is slightly further away from us. Now over here, because we are being asked to consider the effect of some induced current, we can think about using Lenz's law. And Lenz's law states that whenever there is some direction of induced current, that always opposes the cause of changing flux. So the effect of the current induced in coil A would be to try and minimize the change in flux. So first let's focus on this cause of changing flux. If we think about the magnetic flux passing through A, the magnetic flux that is linked with coil A, that must be due to the magnetic field lines passing through this coil. But where are these field lines coming from? Now there is a coil next to it which has a current flowing. Because of this current flow, there must be some magnetic field lines produced by coil B. And we can actually figure out the direction of this magnetic field using the right hand curl rule. So let's say we are looking at coil B, and this is where we are standing. This is right here. This is our eye. And we want to figure out the direction of the magnetic field generated due to the current in coil B. So if we use the right hand curl rule, we can curl our fingers in the direction of the current. And if we look at the coil by placing ourselves to the right, we will see that the current in the coil is moving in a clockwise direction. So if we curl our fingers in a clockwise manner, this is your current I. The direction of a thumb always points in the direction of the magnetic field. So this right here is the magnetic field. Now that means that the magnetic field would look like this. Now because the current is decreasing, the strength of these magnetic field lines will also decrease. So let's write that over here. There is decreasing current, which means there will be decreasing strength of magnetic fields, decreasing B strength. And we can see that these magnetic field lines, they are passing through coil A. So there is some flux that is passing through coil A. There is some flux linked with it. And if the strength of these magnetic field lines, if that is decreasing, that means that the amount of flux that is passing through coil A, that must also be decreasing. So the cause of changing flux is the decreasing current, and finally it leads to decrease in flux through coil A. Now coil A doesn't like that. Coil A doesn't want the flux that is passing through it to decrease. It wants to oppose that. It wants to oppose the decreasing flux. Now to oppose the decreasing flux, it must increase the flux. And to increase the flux, should the coil on the right, should it be pulled or pushed away from coil A? Let's first try and move this coil away from coil A and see what happens. So when we move this coil slightly away, we see that the strength of the magnetic field lines passing through coil A decreases. So that means that the flux through coil A is decreasing. But coil A doesn't want that. Coil A wants to increase the flux. Now if we push, if we move the same coil towards coil A, now in this case the flux through coil A is increasing. So it turns out that coil A must be pulling coil B towards itself in order to oppose the decreasing flux and increase the flux through itself. So in this case, the coils they attract. Now the second question is, what is the direction of induced current in coil A? Now in order to figure out the direction of induced current, we can again look at Lenz's law, which say that the direction of induced current should be such that it opposes the changing flux, the cause of changing flux. Now, if we know the direction of the magnetic field lines generated by coil A, we can again use the right hand curl rule and then figure out the direction of current if we know the direction of the field lines. And I know there must be some opposition to the flux. So the field lines that are generated due to coil A, maybe they should look like this. They are opposing the flux. But But there is a problem. The law says that it should oppose the cause of changing flux. And if the field lines due to coil A, the blue magnetic field lines, if they look like this, then there would even be lesser number of magnetic field lines passing through coil A. These red and blue magnetic field lines would create a net magnetic field in between, and the flux through coil A would decrease further. There would even be lesser number of field lines passing through coil A. But that is not what the law says. The key here is that opposition should be to the changing flux and not just flux itself. So the field lines cannot go in this direction. This is wrong. So let's remove these field lines. Now in this case, the induced current in coil A, that must try to oppose this decreasing flux. So if we look at it this way, we know that the current is decreasing. So that means that the strength of these magnetic field lines, it decreases. So it will kind of start dissipating. You can see them fading away very gradually. And what that does is it decreases the flux that was passing through A. And coil A doesn't like that. It wants to maintain the same flux. So what it does is it tries and supports this existing flux. So it creates a magnetic field which is in the same direction. And that magnetic field looks like this. It is in the same direction. It tries to support the existing flux. Now for the magnetic field lines to move in the direction that is shown, and let's move the field lines slightly to the left so that we can see the arrows clearly. So the current must be flowing in some direction, either from P to Q or Q to P, and then it flows through the entire coil. And we can actually figure out the direction of the current again using the right hand curl rule. So here is the right hand, and the magnetic field lines, they are pointing in the direction of the thumb. So the hand is oriented correctly. Our thumb is pointing in that direction. Now we can notice the curl of our fingers. The curl of our fingers is again in a clockwise direction. And that would mean that it goes like this, just like this, and it goes from Q to P. And that is the direction of induced current in coil A. This is from Q to P. Now let's look at the second example. Now over here we have a wire loop which is reshaped to form a bigger circular loop. And we can see that in the diagram over here. We had a randomly looped wire, and then it has been stressed. It is flexible. It has been stressed to form a bigger circular loop. The direction of the magnetic field is into the plane of the screen, and we can see that from all the crosses over here. Question is to figure out the direction of the induced current in the loop. Why don't you pause the video and first attempt this question on your own? Alright, to figure out the direction of the induced current, we can again use Lenz's law. Is always such that it opposes the cause of changing flux. So we can begin by thinking about the cause of changing flux in this scenario. Now over here the area of the loop is being increased. So let's write that area increases. Now because of that, more number of magnetic field lines now will pass through the loop. So more number of magnetic field lines, more number of B lines pass through the loop. Now if there are more number of magnetic field lines passing through the loop, that will lead to an increase in the magnetic flux. So flux increases. Now to oppose this increase and minimize this change, the coil should try to decrease the flux. It should try to decrease the flux passing through it. Now to be able to do this, there must be magnetic field lines which are coming out of this circular loop, because if that happens, then there will be some flux which is in a direction that is opposite to the direction of the initial flux due to the red magnetic field lines. So the magnetic field lines that are generated or produced must be in a direction outside the plane of the screen. It is interesting to see that in this case, the field lines that are produced are opposite to the field lines that were present to begin with. And those are the red lines into the plane of the screen. This is unlike the previous case, because there the magnetic field lines produced by the coil were in the same direction as the other field. But also in the previous case, the coil was trying to oppose the decreasing flux by increasing the flux passing through it. So to maintain the same flux, the field lines that were produced were in the same direction. But over here, the field lines are trying to oppose the increasing flux by producing magnetic field lines outside the plane of the screen. So the field lines that are produced by the coil, they can either be in the same direction as that of the existing field, or they can be in the opposite direction, but they necessarily have to oppose the changing flux. Alright, now that this coil is producing magnetic field which is coming outside the plane of the screen, we can try and figure out the direction of the induced current. And we can use the right hand curl rule to do the same. So here is a right hand, and the direction of the field is in the direction of the thumb, which is in the upwards direction. Now the curl of the fingers, that gives the direction of the current, and we can see that in this case the curl of the fingers, it is in an anti-clockwise direction. So the current that is induced in the coil, that will be in an anti-clockwise direction.